Let's jump into this one. We've got a particle motion problem, which comes up a lot in AB and BC calculus and in some calculus courses in high school and in college. So if you've got a problem like this, I've got you covered. Let's go. The function x of t equals that thing. We're not even going to, what's the point of pronouncing it out loud, right? It's a juggernaut. It's big. Describes the position of a particle moving on the x-axis. You got a particle moving like this. Imagine a number line, and that particle is just moving to different numbers on the number line, left and right, and those numbers are the position, the where of where the particle is. Where x of t is the position of the particle and t is the time in seconds. So I always like to think before I start a problem like this, what level do I start at? I'm given position. So the derivative would give me the velocity, and the second derivative would give me acceleration. All right. It says find the velocity function of the particle at any time t. We know from our prior studies that the velocity function is the derivative of x of t. So I got x prime of t, and you could say that that's equal to v of t. Just never just write down v of t without writing x prime, because you want to communicate you understand the derivative is velocity. So x prime of t is equal to 3t squared minus, that's going to be 48t, not bad, plus 180. And then the 3 completely goes away. So that's our velocity function. That's it. That's A. Identify the time intervals when the particle's moving to the right. Now I'm going to state out the justification you would write if needed to justify this on a test or on the AB or BC exam. I always start out with my justification first. So the particle will be moving to the right when x prime of t is greater than 0. That's it. That's the justification. Then you go into your math. So let's figure out what x prime is in terms of where it's greater than 0 and even less than 0. So to find that, I need to set x prime of t equal to 0 to find the critical numbers. We're essentially figuring out where x of t is increasing. Okay, so I set the derivative equal to 0. I'm going to factor out a GCF from this. That'll be 3 times t squared minus 16t plus 60. Oh, that's gross, but it actually is not so bad in the end. Got the GCF on the outside, and we've got what multiplies to give me 60 that adds to negative 16, minus 6, and minus 10. Okay, now the zeros of this are very easy. 6 and 10. Nice. So those are my critical numbers, if you will. They're also the places where the velocity equals 0. Interesting. Well, that would be where the particle has stopped moving. So if you're ever asked when does the particle stop moving, where the velocity is 0. Okay, so just like we did in a previous video to figure out in what direction the curve is going, increasing or decreasing, we're going to do the same for the particle. So, and I guess that second arrow should be taken off. And the reason being is we're stopped at t greater than or equal to 0, technically. So we go to 6 and we go to 10. So I'm going to pick a number between 0 and 6 and test it into the derivative. T equals 1. If I plug 1 into this, I'll get a negative number times another negative number. 1 minus 6 times 1 minus 10 is a negative times a negative. That's positive. I'll label this. This is x prime of t. It's our velocity. So what that means is we are moving to the right. So we're moving to the right. So this would be x of t's movement. Right? Now, from 6 to 10, let's plug in, I don't know, 8. 8 minus 6 is positive. 8 minus 10 is negative. Positive times a negative is a negative. Well, if we're moving the negative direction on an x-axis, that would be to the left. Perfect. So negative would be to the left, everybody to the left. And I don't know why I'm singing that, but I am. And then positive from 10 on. How do I know that? 45 is to the right of 10. 45 minus 6 times 45 minus 10 is a positive times a positive. So we're moving to the right. Again, that would be an increase. So that's moving in the positive x direction. And that's it. That's all there is. So since x prime is positive, we're moving to the right. X of t is increasing. Negative, we're moving to the left. X prime is positive, we're moving to the right. So identify the time intervals when the particle is moving to the right. Just draw a little arrow right here. That's going to occur, well, from 0 to 6. 0 is less than t is less than 6. And or, it doesn't really matter, t is greater than 10. Some teachers are okay with an or equal to, others not. On the AB or BC exam, it doesn't matter. Most teachers want the open interval, so no or equal to. But honestly, it doesn't matter. It really doesn't. Okay, so we'll leave it at that. because they're not going to mark you off in the AB or BC exam for either one. If your teacher has a preference, listen to his or her preference though, obviously. All right, letter C says identify the time intervals when the particle is moving to the left. Okay, here's the formal justification in case you need it. A particle is moving to the left when the velocity, x prime of t, is less than 0. And this occurs, now we already have that here. This occurs between 6 and 10. That's it. So the formal justification and then the conclusion. I don't like to write conclusion and then justification second. I want my justification, my explanation to tell me, as well as the person grading me, where to look. It's kind of like when you're giving a speech. You tell the audience what you're going to say, then you say it, and then you write your conclusion and tell them what you said. The reason why you tell the audience what you're going to say is to also keep yourself on track just as much. All right, letter D, last part. Identify the times when the particle changes direction. Well, we already have that. The particle, here's my justification, I'm going to say it out loud. The particle will change directions when x prime of t changes signs from positive to negative or negative to positive. Well, this occurs at t equals 6 and t equals 10. That's it. How do we know? Again, x prime and t went from positive to negative, so the particle went from moving to the right to moving to the left to moving to the right at those designated times. This is just a glorified problem of using the first derivative test, but we're imagining a particle going like this. Right, slowing down, changing direction, slowing down, changing direction. That was awesome. It really was. See you next time.